Good afternoon and welcome to the fourth and final session of today's symposium honoring the scientific legacy of Richard Feynman. My name is Nick Hutzler. I'm an assistant professor of physics here at Caltech, and I will be chairing this session that focuses on new and exciting ways to observe the universe around us. Our first speaker is Sara Seager, professor of planetary science, physics, and aerospace engineering at MIT. Professor Seager is a member of the National Academy of Sciences and a MacArthur Fellow, and her main research goal is to find and identify another Earth, including searching for signs of life by way of biosignature gases in planetary atmospheres. She will tell us about this exciting search in her talk titled Exoplanets and Beyond. Please join me in welcoming Professor Seager.
Thanks, everyone. I'm starting with this picture from Mauna Kea in Hawaii, just showing you a star-studded sky, because we think that every star has planets or a planetary system. And all stars, just to remind ourselves, are suns, and if our sun have planets, it makes sense that other stars do also, and they do. In fact, after wondering about this, humans thinking about other stars and other planets for thousands of years, it turns out that the very nearest star to us, aside from our sun, Proxima Centauri, appears to have about an Earth-mass planet around it. So there are lots of stars and lots of planets out there. And just to convey how many known planets, here's an animation zooming away from Earth. You might not be able to see the white stars, but this is a real map of the sky. The colored ones are stars with known planets. Now, I did not know Feynman, but of course, like every undergraduate student in the world who could, I had a copy of the red book. It was like a paperback, the red books, lectures on physics with the white border and the dark pages that had this weird texture to them. If I could see Feynman today, I would want to share with him that there are truly thousands of stars with planets out there, and that underlying all the techniques that astronomers use to find planets are the very basic equations found in volume 1 of those lectures. And so in exoplanets, we're not using physics to understand crazy new things like at the time helium that's cooled into a liquid and superfluid, but we're using them to explore other planets and to understand what they're made of and the chance of finding life around them. Now, I've stopped this animation at about 1,000 light years, and our Milky Way galaxy is 100,000 light years in diameter. And we heard earlier from Michael Turner that we think our universe has hundreds of billions of galaxies. Our own Milky Way has hundreds of billions of stars. And so if you just do the math and count like how many stars are out there and thinking that almost all stars have planets, surely there has to be planets out there that are like Earth with signs with life on them. And in fact, although the universe is so vast, it's only the very nearest neighboring stars we have access to study in detail. And I'll come back to that. So the first thing we do in exoplanets is just take all the planets we know and plot them on this diagram. It's called, we just say it's the, in this case, I'll tell you what this is. It's showing you planet radius. It's on a log scale, so Earth would be here at 1 Earth size. This is 10 Earth size. Jupiter's about 11 times the size of Earth. On the bottom, you see semi-major axis, also on a log scale. So Earth would be here at 1. You have Neptune and Jupiter. And all these different colored points are planets. It's not all the known exoplanets. It's just the ones that have like a semi-major axis or properties that I could put on this diagram. But just look at how this diagram is so full of planets. That actually, there are planets that are 100 times, more than 100 times closer to their star than Earth is to our sun. And some of these planets would be, some of them are small rocky planets that would be so hot as heated by their star that their surfaces are hot enough to melt rock. It's just like those horror stories we're hearing about Hawaii today. They wouldn't have volcanoes erupting necessarily, but the surfaces would be so hot that there would just be liquid lava lakes everywhere. There's a whole bunch of planets in here that appear to be the most common type of planet in our galaxy, 2 to 3 times the size of Earth. And in fact, we don't really know what those planets are. There's no solar system analog. They could perhaps be water worlds, 50% or more water by mass, like scaled-up versions of Jupiter's icy moons, or they could be giant rocks with hydrogen envelopes. We're not sure. Now, it's fair to say here that this dark part of the diagram is dark because our techniques don't reach there yet. And I just have a little bit of a crazy slide. You don't have to follow this slide. I kind of condensed half the semester's like undergraduate physics class on this slide because I wanted my physics professor and graduate students here just to know that it's a very great subject, pedagogically speaking, because you can work out fundamentals from first principles for underlying every planet finding technique. And I've just sort of listed some of them here if you wanted to browse them. I've just sketched out some selection effects, because some only techniques work for some types of planets and not others. And I'll come back to one or two of these things a bit later. But for now, it's just fair. Oh, and one more thing I wanted to say was that, you can overanalyze this, but don't. Like, for example, you see one population here and another down here. These are transiting exoplanets found by ground-based searches, which, because of the blurring effects of Earth's atmosphere and the day-night cycle, can only find big planets close to the star. The ones down here are found by the Kepler Space Telescope, small planets. And this is actually, they haven't found big planets because these smaller planets are 10 times more common than Jupiter-sized planets. But our takeaway from this plot is that in exoplanets, in terms of the types of planets out there, anything is possible within the laws of physics and chemistry. And it turns out in exoplanets as well, it's an interesting field because the line between what is considered mainstream and what is considered crazy is constantly shifting. And you couldn't have had this talk 20 years ago. So just a smattering of planets, all by the radial velocity technique, if you were paying attention back then. The planet and star orbit their common center of mass, and astronomers measure the Doppler shift of the star and infer the presence of a planet. And now there's so many techniques and so many planets, the field is really so rich. Well, let me move on to another summary diagram. This one is putting planets that we can measure the mass and the radius. And so effectively, we can have an average density. And two different techniques have to be used. One could measure size and one could measure mass. And here I'm also showing you a log-log plot. This is showing you planet size. Now I have the scientific notation. Earth and Venus, Uranus and Neptune, Saturn, Jupiter. And this is planet mass. So here, by the way, to any planet-finding technique that we have, Earth and Venus would actually appear basically the same. Now, what I'm showing here are curves for illustration of constant composition. So imagine for a moment, it's purely for illustration, there was a planet just made of iron. And as you would imagine adding more mass to like a giant sphere, you might expect it to increase as r cubed, which it does initially, but as more and more mass is added to this hypothetical planet sphere, the interior starts compressing. And that compression means that it doesn't, and eventually, if you added enough mass, it would flatten out. Now, each of these points are planets, and I just wanted to put up a few equations because I looked around the room, and I think actually like 90% of you could try to infer what planets are made of based on their mass and size with this sort of simplified set of equations: mass of a spherical shell, hydrostatic equilibrium, where the pressure gradient force is balanced by gravity, and all the physics is buried here in the equation of state, how the pressure, temperature, and density are related in thermodynamic equilibrium. And in this field, actually, we have to get these equation of states, which are unique for each material, by experiments or density functional theory, computer simulations, or very high pressures. We can assume all electrons there's like a sea of electrons surrounding nuclei. But I was just reading the news from the other day in exoplanets, and a team used the laser ignition facility at LLNL, and they went to like, I want to say 2 terapascals or 1.4 terapascals. That's like millions of atmosphere pressure that we have here with iron. And they do these like experiments with lasers, and they heat it up just for like a nanosecond to measure the material, just to sort of get the properties of iron and other things at high pressure, so we can use it to understand the range of what planets could be made of. I just want to tell you that because in exoplanets, we don't inspire new physics, but that's one example, maybe like one of the only ones where we do inspire new experimental physics. And so on this plot, you can see all the planets, and there's some really interesting things going on here. Here, you can see that there are planets of the same size, spanning 2 orders of magnitude in mass. And these are giant planets where the very massive ones, what's happening is that in their interiors, there's very high pressure. I like to call the atoms in there pressure ionized, where electrons are popped off at high pressure, and the nuclei can squeeze closer together. So even though the whole planet is more massive and there are outer layers The planet is getting bigger. On the inside, it's getting compressed because the nuclei can squeeze closer together. And so the planets are of the same size. We also have planets that are the same mass that are very different in size, Jupiter-sized planets, some that are almost twice the size of Jupiter. And we write down the equations that describe how a planet, when it's formed hot and somewhat big, contracts and cools as it ages. As the energy the planet is formed with, the gravitational potential energy from when it formed, it slowly escapes out, the planet contracts and cools. We don't know what the missing energy source is that's keeping these planets very inflated. Now, there are several theories, and there's probably people in this room who work on it. Everyone has their favorite theory. Probably, nature is most certainly smarter than we are, and it's probably a number of different reasons about why that is happening. By the way, there are no planets in this part of the diagram because the planet wouldn't be gravitationally bound. It would be too low density for its gravity. There aren't any here. I was always hoping to find a planet that would be like 100 times Earth mass, like a giant, massive rocky world. But so far, nature doesn't seem to make them. It seems to make rocky planets down here that quickly, as they get more massive, appear to have accumulated gas envelopes to make them lower density. I forgot to mention what these curves were. This was pure iron. These would be silicates. This is water. And this would be like cold hydrogen. And anyway, one more thing was there are all these planets here. We're not sure what they're made of. It's somewhat ambiguous based on their mass and size and kind of where they fall in this diagram. My plot is unfortunately somewhat out of date. In this box here, I'm showing you planets that would have high enough density that they would follow along these curves here of silicate or silicate and iron. And they actually would have to be rocky planets based on their average density. And sometime you could take this for fun and work through no matter how you slice and dice this, there are definitely rocky worlds out there. And in our whole search for life and the thought of life on other planets, we want to start with rocky planets that have a solid surface as we know it. And that's where we're headed. So just to summarize that first part of my talk, exoplanets are diverse, covering nearly all masses, sizes, and orbits possible, so far that we've been able to find anyway. Small rocky planets are common. Oftentimes, little can be known about an individual exoplanet. I'm clearly giving you a very high-level, rapid-fire summary. But sometimes all we know is the planet size and orbit, and that's it. And so our goal is to learn more about planets. And in this case, the transit technique is very powerful. You can get a mass and a size, and you can also study the atmosphere. And in the search for smaller and smaller planets right now, I wanted to just show you one of the reasons why transiting exoplanets are so popular. Now, it turns out that Earth's size, compared to our sun's size, radius, the size ratio is about 1 part in 100, Earth to sun size. So if you square that, you get the area. That's about 1 part in 10,000. And this little drop in brightness you're seeing here, if you could imagine measuring a star's brightness as a function of time, the brightness drops by a tiny amount. This is the planet to star area ratio. So for an Earth transiting a sun, that's 1 part in 10,000. And I guess, I don't know if everyone here is like a theorist or modeler, but I know there's some experimentalists. The question is, do you have to measure things to 1 part in 10,000? Or would you want to? It turns out Earth is 300,000 times less massive than our sun. And in terms of reflected light, it is 10 billion times fainter. So which would you work on if you wanted to find another Earth? Would you do transits at 1 part in 10,000? Radial velocity for 1 part in 300,000, or would you do 1 part in 10 billion? Well, it's always more fun to do the harder one, of course, so hopefully I have time to get back to that at the end of my talk. Now, in fact, astronomers in exoplanets, we don't use the phrase like, there's plenty of room at the bottom. We actually have another phrase, it's called the race to the bottom. And by that, we mean the bottom size of stars. Because it's not just that a planet, I've drawn this fake planet on this real image of the sun, and the same size planet on like a sketch of a star, a small red dwarf star, that is 10% the size of our sun. This is the smallest type of star pretty much possible. Any smaller and colder than fusion wouldn't happen inside the star. And actually, a group of astronomers went out purposely to search these very smallest stars and took like the 20, like say, brightest of these very small dim stars, and actually found, and by the way, I just put this number here, so for our own Earth sun, it's 1 part in 10,000. For this one, it's 1 part in 100. And the probability to transit, because we think that planets, their orbits and the star's rotation axis is just randomly distributed. So the star and planet have to be lined up just so perfectly to see a transit. And the further away the planet is from the star, the lower the probability for it is to show transit. So if you wanted to find a transiting Earth, probability to transit about 1 in 200, and if every star had an Earth, every sun-like star had an Earth-sized planet in Earth-like orbit, you'd have to look at least 200,000 stars to find one. But for these TRAPPIST planets, it's only 1 in 30. And in exoplanets, there is a lot of luck. I don't know, nature has been bountiful for us. And these astronomers who went out and just only looked at 20 stars as a pilot program, they found this fantastic system called TRAPPIST-1. I don't know how many of you have heard of TRAPPIST-1. It's actually, you know what the real name of it is? TRAPPIST. This is why people rename it, because it was called 2MASS J23062. Yeah. It's a bit of a mouthful, but many of these stars are already known in catalogs, and they already have a catalog name. Now, for those of you who want to peruse the gorgeous transit light curves, you can. For those of you, I wanted to show you this cartoon showing you that the star is so small, it's almost the size of Jupiter. And remember what I told you about compression in the core, which is why it can be the same size in a very different mass. Here's our sun for comparison. And these planets are blank, kind of indicating that we don't really know anything about them. Although, if you read the popular news, one day, hey, there's definitely a chance for life on them. Another day is no, there's no chance for life, they probably have no atmospheres. Another week, the news would say, hey, these are water worlds. They probably don't have chance for life because if you imagine a pure ocean world, there may not be anywhere to concentrate nutrients, concentrate like the ingredients for life. And so the debate kind of goes on. We really don't know much about it. Now I do I do a lot of different types of work, and sort of a fair amount of it would be on exoplanet atmospheres. We're not sure if these ones have atmospheres, but instead of telling you about like my computer codes and more details, let me take a little mental break and take you on a virtual trip to a planet orbiting an M-dwarf star. Now, there are lots of M-dwarf stars people are searching, and there are many, many known exoplanets around small M-dwarf stars. The stars are anywhere from 10 to 50% the size of our sun. So first of all, for some of these planets, I forgot to mention that for these planets, the planet has to be relatively close to the star because these small stars have very low energy output. And so if you want to think of a planet in the so-called habitable zone, where the planet as heated with a thin atmosphere, as heated by the star, is not too hot, not too cold, but just right for life. It's relatively close to the star. And actually, by Kepler's law, then the planet would go around the star fairly rapidly, like these TRAPPIST planets have periods of just a few days, a few to 10 days. So if we could go to one of these planets, the star, the sun, might be very big in the sky. But because the planets are so close to the star by tidal interaction with the star, the planet has most likely evolved to its most lowest energy state, which is tidally locked. Every time the planet rotates one time, it also orbits once, just like our moon does with Earth. Our moon almost always shows the same face to Earth at all time, but actually a little more than half because it has this libration. So what that would mean if we could go to this planet is that the star, the sun, would be in the same place in the sky at all times. So you could choose to visit where it's always daytime, or where it's always night. Or for me, I'd go to where it's always sunset so I could see a very long green flash. So on this planet, because of Kepler's law being so close to the star, a year would be, let's just say, about 10 days. And for any kids in the audience, I saw one patiently sitting in the back. Your birthday would be every 10 days. Now, on the other hand, maybe visiting this planet wouldn't be so great because the stars have flares. They have like bursts of energy, of high energy particles that would be very damaging. What kind of sunscreen would you bring? You might get like mutations. For those of you glued to your phone, that wouldn't be a good idea because the high energy particles would destroy the electronics on your phone. So we're not really sure about these planets. They're the easiest way for us to find planets where we can search for life. But it turns out that the very energetic flares are a concern. They always kind of have been. We kind of sweep it under the rug because it's easier to find planets around these stars. Now, how many of you have heard of the Carrington event? Yeah, in the 1850s, astronomers were first realizing there was some connection between star and our sun and magnetic field and events on Earth. Actually, there was an astronomer, like an amateur, quasi-amateur professional astronomer named Carrington. Apparently, he couldn't get like a job at an observatory, so he used his own money from his family's brewing company. And one day, he was studying the sun, and he saw it brighten around a sunspot. And about a day and a half later, our Earth became electrified. There was an induced current because part of the sun was ejected, a small part with its own little magnetic field, and it hit Earth. And at the time, telegraph operators, they could take the batteries out of their telegraph, and it still worked because the air all around was charged. Now, at the time, astronomers didn't disseminate their information yet. They didn't totally understand the connection between the sun and that, and Maxwell's equations weren't yet articulated, so people didn't totally know what was going on. But I forgot to mention, the northern lights were seen almost down to the equator. It was this incredible event on Earth. And people do worry about it today, because if we get another event like that, today we have our power grid, which wouldn't fare so well under those conditions. Now, back to TRAPPIST, the Kepler Space Telescope was looking at a field for 80 days that included the TRAPPIST star. And astronomers found that it had 40 flares in 80 days. And they only estimated, because Kepler's like white light, but most of the energy in these flares comes out at much higher energy, that one of those events in 40 days was equivalent to the Carrington event. But the planets are so close to the star, they're much more likely to intercept it. So with that in mind, I don't think we'd want to visit the planet at all, and I'm not sure if these planets are going to have life or if they even have atmospheres. Says, sorry, bro. So to do more on exoplanets, and to learn if they have atmospheres, and we could correlate that with the star's activity, we want to learn more about planets. I already showed you this diagram. And now I'm superimposing on it stars where we have observed atmospheres. This isn't like totally accurate because the plot is made just from like querying a database, so I didn't go back and double check every last one that it was right. But you can see the ones with atmospheres fall into certain categories. They're the transiting planets, where the planet goes in front of the star, and they're directly imaged planets where we can block out starlight and see the planet directly. And right now we're pretty limited to just certain types of planets. And I wanted to just say that when I think of the search for life, I divide it up into transits and to direct imaging, because those are the types of planets, the atmospheres we can see. For transits, we pretty much have to go to space above the blurring effects of Earth's atmosphere. And for direct imaging, it could be ground or space. Now let me briefly tell you about exoplanet atmospheres. And you can see on the left there a cartoon showing you the atmosphere. It's like a very exaggerated atmosphere of an exoplanet. And here, the starlight can shine through the atmosphere. And just like shining a flashlight through a fog, some light makes it through, some doesn't. I just put this equation for anyone who remembers anything about radiative transfer, but essentially there's light going through. It gets exponentially attenuated if there are molecules absorbing. But for our purposes now, conceptually, just think about the planet. If it's transparent, it's a certain size. And if there's a wavelength where the atmosphere is blocking the starlight from getting through, the planet looks a tiny bit bigger. And that's kind of what all of transiting exoplanet atmospheres is based on. And so in that regard, how big that atmosphere is really matters. And I only picked one real data set I kind of cherry-picked one example to show you of an atmosphere, and let me walk you through this. This is showing you the transit depth, so how deep the transit is, and this is wavelength in microns. This is showing you visible wavelengths here, near-infrared here, and this is a little further in the near-infrared. And this would be Spitzer Space Telescope. The rest of this is Hubble Space Telescope. Now, what you have to do is think that if the planet had no atmosphere, or if it had clouds and we couldn't see an atmosphere, then this would just be a straight line. So I think you can all agree with me this is different from a straight line. And you can see here the planet is looking bigger at certain wavelengths where the atmosphere is absorbing. And this is one of our very best data sets in exoplanet astronomy of a atmosphere. And this is giant water vapor features. Now this planet is just an it's called a hot Saturn. It's a very low density planet. Saturn is about 0.67 grams per cubic centimeter in its average density. This one's even lower, more like 0.2. It's a very puffy planet with a giant atmosphere, and that makes it relatively easier to observe. Now for exoplanets in our search for life, we do have a plan, myself and the whole community working on this, and that's the James Webb Space Telescope. We want to use the James Webb Space Telescope to study atmospheres like in this plot, but for smaller and smaller planets, down to Earth size, going in front of M-dwarf stars. And actually, we have this mission. Look, did you see this little telescope? It's actually not that little. It's bigger than, it's about my height and about this big. It's called TESS. It's an MIT-led NASA mission, Transiting Exoplanet Survey Satellite. We call it the Finder Scope, because it's going to find planets. And all the planets it finds that are suitable, the whole community will be using the James Webb Space Telescope to follow up. Actually, it had a spectacular launch on April 18th on a SpaceX Falcon 9 rocket out of Cape Canaveral. And the plume was burning so brightly, and the rocket just went, it seemed like it was going on forever. And Tesla's going into a very unusual orbit. It's a highly inclined, highly elliptical orbit about Earth, where its final perigee will be something like 20 Earth diameters away, Earth radii away. And it'll like have this, so it can spend 13.7 days, most of it, away from Earth, where the reflected light and heat from Earth won't be bad for observing. It's a brand new orbit for observations. Okay, so in the search for life, we're not there yet, but we hope to get atmospheres of small planets. And on Earth, it's oxygen, our best gas that we have. Our atmosphere is 20% by volume oxygen, but without plants and without photosynthetic bacteria, we would have no oxygen. And I'm going to take a little aside for a second and talk about something not related to physics or exoplanets, because I embarked on this problem, and I think it helps to show like the sort of wonderful journey of exploration that we all get to do. So I work on exoplanet atmospheres, and the question is, could there be any other biosignature gases other than oxygen that are really great indicators of life elsewhere? And when I was doing this, I had this crazy theory. How many of you get emails about crazy theories? I know a lot of you, probably all, almost everyone, right. Well, I had my own crazy theory, not in physics though, but in chemistry. And for a while I thought, you know, what if life makes all gases? Because it turns out in our atmosphere, every gas to the part per trillion level actually is produced by life, although it usually has a dominant source that is not related to life. So I went through my limited knowledge list, and it turned out that was so. So who does the MIT professor go to with a crazy theory? Well, I had to go to the next level up, which is a Nobel laureate. So I went to Jack Szostak. He welcomed myself and my two biochemistry colleagues, and within about 10 seconds, he came up with a counterexample and crushed us. So we went back to the drawing board, and we did like a big data fusion, data gathering project, wrote combinatorics codes like they do in drug discovery to like seed molecules and make them bigger and bigger. And we came up with a list of 14,000 molecules that are all molecules, they couldn't be like exhaustively, but nearly complete list of molecules that are in gas form at room temperature and pressure, as well as like a more giant database from scouring the literature and scraping all the websites possible for all molecules made by life. And what we found was actually even more interesting, which my brilliant postdoc Janusz Petkowski found, was that actually it turns out that life has very specific patterns. Even though out of those 14,000 gases, life produces only about a quarter of those, it actually has very specific types of molecules or fragments of molecules we call motifs that life entirely avoids. And I've taken this kind of detour now to explore with my team why that is. And in some cases, we're working to explain it away with this sort of thought about there could be inroads into origin of life and toxicity and maybe even drug discovery. So it's my favorite thing. I wish I could have spent my whole talk talking about that, because it's my main thing that I've been working on when I actually get to get on my computer and do some coding. So in the search for life, I only have a few minutes left, so you know, transits are only the first part of a long story. They're very limited because you have to have this fortuitous alignment. And it's limited to small stars. I didn't talk about that, but because this atmosphere, annulus superimposed on the size of the star, is the problem. So there are many other ways to find planets. To study atmospheres, and each one is crazier and more sophisticated than the last. We have giant ground-based telescopes, the 30-meter telescope, which is a huge, huge telescope. It will be able to study planets directly imaging them, M-dwarf planets like Proxima Centauri, our very nearest star, which has a planet that is not transiting, and will be able to block out the starlight. And what I forgot to mention in my talk is that here at Caltech, there's like, half a dozen expert exoplanet astronomers, one pretty much per slide of what I talked about, working on these problems. And we have even crazier idea that I wanted to share with you briefly. It's called starshade. And starshade is a giant specially shaped screen. Here you're seeing an animation of the starshade unfolding, getting unfurled from its stowed position with this truss opening up and these petals snapping into place. This was conceived of in the 1960s by Lyman Spitzer. And he worked out all the math to show you that you have to use the starshade's special shape for diffraction to block out the light from a point source star so you don't have the airy ring pattern destroying your image. And actually, it was revisited every decade in some form or another until today, when we actually think it's possible to build it. And there's a lot of people working on this right now, but here's a picture of myself and a couple of team members at the JPL laboratory. It's also, there's another version of starshade made by Northrop Grumman Corporation. So I wanted to end my talk with, let's call it prediction or forecast. And here, by the way, we're zooming out from that same animation to now fake image of our galaxy. And I know someone's going to ask, like, why are the planets in that specific shape? It's purely selection effect reasons. The Kepler Space Telescope looked in a certain direction for 4 years, so there's a lot of planets in that direction. Microlensing involves the bulge, which is highly densified with stars. It's a very low probability kind of event, so you need lots and lots of stars to search for, and that's why it's there. So in this field, it is somewhat easy because we know small rocky planets are very common. They're basically everywhere. We know with the James Webb Space Telescope, because it operates at near infrared wavelengths where molecules are active, we'll see water vapor. It pretty much has to be around because water is a very common, hydrogen and oxygen are very common. It's locked away in minerals. It just has to be in planets. So I believe that with the James Webb, we will see planets with water vapor. Actually, it turns out that any college student today was born when exoplanets were first discovered, or later. And so to people today who are in college, it makes sense. Of course there are exoplanets. And so we hope to have a future, 10 years from now, where people say, of course there are planets with water vapor indicating water oceans. And so 30 years from now, and that's kind of a long time, but I have to be conservative, hopefully, we will have planets where we see signs of oxygen in addition to water and other things, where we may not be sure that there is life out there, but it'll be enough to kind of keep the search going. It's like a multi-generational project. And finally, just while I wrap up, I did want to give something even more speculative, but in some ways, like, my job is really hard, but in other ways it's really easy because we have these big telescopes. We know how to build things in space and large telescopes on the ground. But if we don't find anything in that really tiny space of just, a few hundred light years or tens of light years, the next generation will have a whole new set of they'll have to have like a paradigm shift entirely. They'll have to have self-assembly in space or printing things in space. Figuring out ways to scale up to search even more stars is going to be the way that they're going to have to do it. So to finish, just to summarize, we know of thousands of exoplanets orbiting nearby stars. Small rocky planets are very common. And the next generation telescopes will study small exoplanets and atmospheres for the search for water and biosignature gases. Thank you.
Thank you, Professor Seager, for that very interesting talk, and I'd like to open it up to questions.
Thank you for a really, really clear lecture. I feel like I learned a lot, which led to some questions. The first one is, why is the Earth so unique in that first plot you showed of math? It looked like it was kind of on its own.
Earth is definitely on its own because right now our techniques can't reach there yet. Earth is so small and low mass, and it's so faint compared to our sun, it's nearly impossible to find. We're just lucky that nature provided so many different planets. Most of the ones we find are either big planets or they're small planets orbiting small stars.
Okay, and in the next slide on the mass versus size, it looked like all of the predictions that came from a sort of single, like iron planet and so on, were much flatter than what the reality of planets is. So why is it that planets change in that different kind of curve from what it would be from a single composition or constant composition?
Well, it appears that when planets form, the sort of very hand-wavy bigger picture is that they accrete rocks, and gas, rocks and dust rather, and once they get to a certain mass, they start to accumulate or suck in, based on gravity, all the gases around them and start growing. So people just think for some reason the planet stalls out at a smaller size. It won't just keep getting more and more massive. It has to somehow have volatiles either outgassing or being collected from the nebula. We don't have a great answer. That's the best we can give you.
And how do you measure the mass? You made very clear how you measure the size, but
right, I couldn't tell you everything. Mass is measured in most cases by the Doppler method, it's called. The planet and star orbits the common center of mass, and astronomers can measure the line-of-sight motion to literally walking speeds of centimeters per second. And they have to infer the mass. It would take too long to work through it all. But it's the effect of the mass making that planet wobble that we can measure mass.
Last one, why does the locking happen? The moon locking that you described also happens in some of these planets.
It's because the planet, there's tides interacting. So imagine that you have the star and okay, it's going to be hard to answer this really quickly, but you have the star and the planet. And the planet actually elongates just a tiny bit. But then the planet's rotating. So now that's elongated, but it wants to pull back. And so over time, that just kind of makes it lined up, so it doesn't have that extra energy problem.
So in one of your earlier slides where you're plotting mass against radius, I noticed at some point with the curves, it got to the point where increasing mass will actually decrease the radius. Was that just an artifact of the data, or could there possibly be planets where they have such a high mass that the radius starts to decrease?
I always show that plot to physicists because they always have a lot of questions about it. There's probably no planets of that mass, actually. But it would actually decrease. There are things called white dwarf stars. You know that when you basically keep adding mass and eventually it becomes like all neutrons and it's super dense. So yeah, if you could actually, it would be something else. But there's probably no planets there. We'd probably have to call it something else if it was in that regime.
Okay.
You mentioned that oxygen and methane are signs of life in a planetary atmosphere. Is it preposterous to think that in 30 to 50 years, looking for exotic signatures of industrial contamination or even the exhaust of rocket fuel might be a possibility of narrowing down the scope of investigation of planets?
Yeah. People love the thought, and like on our planet, we have chlorofluorocarbons and sodium lamps and other things. It could be possible in the very far future, but you have to think about those lines are extremely narrow. And they don't have, like, oxygen is this giant signature. It's very spectroscopically active, and there's a lot of it. So if we can find a way to do very, very, have a huge, huge collecting area, it may be possible sometime in the future.
From a biologist point of view and an evolutionary point of view, I'm very aware of how the Earth's atmosphere has changed across the period when life originated on Earth till what it is now. And certainly the oxygen level is way higher now than it was earlier. So I'm just wondering how much your search for life-permissive gases in these atmospheres are really informed by this deep paleontology about what was going on in the Earth's atmosphere a long time ago, and also some of these sulfur bacteria and so on like that, which obviously don't need oxygen.
Astronomers now, it's kind of like what's called a toy model or a cottage industry. We'll put anything in our model that we can. So we do rely too heavily on oxygen. We're very terracentric. It's a bad habit.
Modern terracentric. Modern terracentric.
Pardon me?
Modern terracentric.
Modern terracentric, yeah. No, we certainly do consider everything we can. It's tricky, though, because all the small things like hydrogen sulfide and methane, all these small gases that microbes do make, they're making them by exploiting potential chemical energy gradients. But if there's any way to catalyze a reaction that life uses, probably somewhere else on the planet, just based on the different temperatures and pressures, it would happen anyway. So hydrogen sulfide comes from volcanoes, and methane is coming out of mid-ocean ridges. So we struggle to think of which environment could these gases accumulate and be meaningful. But yes, that's a whole huge field of growing research now to sort through false positives, even in the case of oxygen and all these other gases and other times and other atmospheres.
Thank you.
So.
Yeah, and maybe I'll wrap up with a quick question.
I haven't got my favorite question yet, so I hope you're going to ask that one.
Oh, geez. Do you happen to recall Jack Szostak's counterexample?
The thing is, I can't recall what it was.
Okay.
It was just
something weird.
It was some hydrocarbon, but do I have 1 more minute?
Absolutely.
Okay, so I'm sure that you would all have done the problem the same way I did, because I was doing this combinatoric seed molecule, and I took the big 6 biochemical elements: carbon, nitrogen, oxygen, sulfur, phosphorus, hydrogen. So I just took each of the 6 and I paired them in all possible ways. But I have to make sure that they're, I don't have a missing electron gap. I have to make sure that it's neutral, and then we do some other tests to make sure they actually exist, by scraping websites or trying to figure out if they're volatile. So that's what I did. And he said, first of all, that's totally wrong, which is what one of my colleagues had said, who I didn't listen to, because nature doesn't do it that way. Nature would do the combinatorics on everything but the hydrogen. And then hydrogen gets populated at different valencies. So for example, you could have carbon that would have a triple bond and just 2 hydrogens. Or you could have hydrogen with a double bond and 4 hydrogens, or hydrogen with this. And so nature would do it that way. And so I had done it totally wrong, and I had kind of created my own universe of selection effect. So I had to tell my colleague he was right, and then go back to the drawing board on it.
And one final quick question.
Thank you. What about looking for signs of civilization, at different levels of light, light of cities? Because you see those planets quite well in the orbits and the transits. So could you look for different inhomogeneities and light levels and things like that?
So right now it's completely out of the question. And normally I would just sort of go on and say, except in the spirit of the conference and what I said before, that the line between what is considered crazy and what could be mainstream is constantly shifting. And so all of these ideas that you've mentioned, people have, believe it or not, written papers about it. In that case, it would be quite hard to do because the light from these cities would be so tiny. Plus now, for people who like astronomy, we have like full cutoff lighting. So eventually they may evolve to a way where they don't have like light that's just leaking to space.
All right. Let's thank Professor Seager again for a very interesting talk.